Welcome, everyone. Thank you for joining our digital Q&A session with Dr. Maria Kovaleva. Before we begin, I would like to acknowledge that I'm speaking here from the traditional lands of the Kaurna people of the Adelaide Plains. I recognise their connection with the land, waters, sea and skies, and I pay my respect to the elders past, present and emerging. I also extend those respects to all Aboriginal and Torres Strait Islander peoples here today. My name is Lucky Gira. I am a space communicator at the Australian Space Discovery Centre here in Adelaide, and today I'm being assisted behind the scenes by Georgia Dallimore, who's another space communicator. If you have any questions during our chat today, please submit them through the Q&A function, and Georgia and I will pass them on to our guest, Dr. Maria. And we invite you to stop into the Australian Space Discovery Centre, drop in, and you can get the opening hours from our website. So today, our space guest is Dr. Maria Kovaleva, joining us today from, Maria, where are you joining us from today?
I'm from Perth. I'm connecting from Western Australia. Hello, everyone. It's my pleasure to join you.
Amazing. And what have you been doing there?
So I moved to Western Australia in 2019 because I got a position of a lecturer at the Curtin University Centre of Radio Astronomy, which is actually goes under the umbrella of ICRA, which is International Centre for Radio Astronomy Research.
Amazing. And so I've looked a little bit at your career and what you've been up to, and you've had a really interesting career. You started out as a radio antenna designer overseas, and then you are now working as a lecturer at the International Centre for Radio Astronomy at Curtin University. So what first sparked your interest in this field?
Well, it's actually an interesting story, because when I started, originally I'm from Russia, I'm from Moscow. I grew up in Moscow, and when I was a school student, I really liked physics, and I also liked arts, and I had no idea what I wanted to become, but I just followed my curiosities, my passions. I also did lots of dancing, and physics teacher that I had was very demanding, so I had to spend a bit more time in physics to do well at school. And I also helped my peers, my friends, with some assignments. I was spending time after school explaining them the homework, and it was the reason actually that I decided to go to the university, which is an engineering. So I graduated from the Moscow Technical University of Communications and Informatics, specializing in the communication with mobile objects. At that time, I started in 2006. There was no 5G, and phones were used by, those button phones.
It was the Nokia phones.
It was, I had an understanding that it's something that will stay with us. It's a career in the telecom will stay with us because it's just something that's picking up. And also it was interesting. But I also really, after getting to uni, I still was fascinated by something that's art. And turns out that antennas remind me art, and this is why I really like this field.
That's incredible, because just the fact that you're focusing more on art, and then you've got art, physics, and then you've become an engineer. Most people wouldn't see that as a natural, I would say, linkage or pathway between the two. And so what does an antenna design engineer do, for those of us who don't know? Just a very quick summary.
Electromagnetics is considered the hardest subject in the whole curriculum of becoming an electronics engineer or electrical engineer. And the difference between electrical and electronics is just the amount of power that you put in the device. And antennas are front ends of the systems that transmit or receive information. So to make the system efficient, so that it actually captures the signal, we have to model it in the, it's called CAD, computer-aided design, lately in the last, let's say, 10 years, because the computers are becoming so powerful, and the codes are developed to actually solve the Maxwell's equations. So I don't have to do it myself. I wouldn't be able to. Yeah. We use a specialized software that we create a digital twin of the antenna. Mm-hmm. And we run the codes to actually predict its performance. However, it doesn't end on that, because we cannot just rely on the codes. Sometimes there are mistakes. You can, as an engineer, you can make a mistake in the software, and you're getting some performance, but it's not a real one. So it's an essential, like, second part of the project is you have to actually manufacture the prototype and go to the lab and measure. So in this slide that you're showing, and the top left picture, I am at the anechoic chamber, which is stands for the no radio frequency interference and no reflections of radio frequency in the chamber. So it simulates the perfect free space, meaning that the antennas that are tested there, they have the most realistic performance compared to the simulation, because we simulate in the free space assumption. However, depending when you place those antennas, things change. So it's another aspect you have to also consider, whether it's a car, it's an airplane, or it's a handheld device. Things change depending on where these antennas are placed.
Yeah, so it's really interesting, because my understanding is that, like you said, it's essential that the antenna design engineer, it's essential for your expertise is essential for expanding like wireless networks, satellite systems, development of advanced Internet of Things or IoT devices. From, like, I know you mentioned when you started there was no 5G, but now that we have 5G, there's also space exploration. And you could say that your role was pivotal in keeping people and devices connected. But how did you always start out in the space industry, or like was that a gradual transition? Could you share with us how you went from being an antenna design engineer to now your current role as a lecturer working in radio astronomy?
So I remember reading about radio astronomy when I was a student in Moscow. So I was an undergraduate student, and it just blew my mind how there is a visual spectrum of electromagnetic wave, which is narrow. And I always was fascinated by the planets and black holes. But when reading about radio astronomy, I realized that it's not only that we can study space in the optical spectrum, but also in other ones. And not only radio, it can be X-ray. And but at that time, there was no opportunity to work in that field. I was not seeking for it. After graduating from university, I joined the Russian Space Systems to become where I was an antenna designer. And my antennas were placed on the aircrafts as a search and rescue devices. In the case of emergency, the antenna would send the emergency signal to the satellite at 400 megahertz, and then it would be a distress signal. Then from the satellites, there would be a signal back to the operation on Earth, and they would send the rescue team to the place where there was a potential crash, for example, of the airplane. And then there will be another frequency that antenna communicates at, which is a lower frequency, about 100 megahertz, to actually help the rescuing helicopters to locate the exact position of the distress. And I worked there for 3 years, and it was a really good job, because I could see the progression of the idea from what kind of antenna can be used, and to the small production. There was a small production there were technicians, and I could really see the entire cycle of the engineering. That was really educational for me. And then I moved to Australia to do my PhD, and I don't know, I never planned really to go anywhere overseas, but I have heard about an opportunity, and I thought, why not? I just can try. And I got a scholarship.
Yeah, amazing.
Yeah.
Amazing. So that's pretty amazing that you started out, I guess, at the beginning of your career doing one thing, and then over time and through, different opportunities came up. So in your current role, could you give us a day in the life. What does a day in the life as a lecturer at Curtin University at the International Centre for Radio Astronomy, what does that look like?
I love my job because every day is different. I do have teaching a lot, but it's not a lot of my time. I do co-teach, so I prepare lectures and I go and physically teach and work with students. I also supervise. So when it's the time of the year when there is a semester happening, a few hours a week, I actually interact with students. I help them with the lab. I have meetings. All the rest of the time is my research time. And I start as normal, and then I open my emails, and then I see if there is any urgent work that I need to do. If there is no urgent work, then I go to my codes and I think of what else I can investigate to have this work published. Also, I perform electromagnetic simulations for the square kilometer array. I'll tell you later a little bit about it. Right now it's under construction, and there are still quite a few frequencies that need to be simulated because to observe, we need to have the beams of the antennas. So they are being produced right now. There were a few changes in the last few years with the arrangement of antennas that will be a part of the SK. So I had simulations. I've been doing them for the last 2-3 years. And I usually split my day in 2 halves. In the first part, I addressed, as I said, immediate issues. And in the second part, after lunch, I try to focus on writings. To progress research, it doesn't happen every day that I come up with something new. But for example, there is always a conference deadline, or I know there will be in a month. So I think of what is it that I need to prepare, which figures I need to create, so I could communicate the information.
That's really incredible. I mean, it seems like you've got such a diverse set of duties as your job. Like you said, you mentioned that you are a lecturer, you're also a researcher. I think you touched on that you also work with the Square Kilometre Array, which for those of you who are listening online is actually going to be, I think it's the largest radio telescope that's going to be, once it's built, it's co-located in Western Australia as well as South Africa. And it's going to really help us look out into and learn about the origins of the universe, which is pretty incredible. But I also noticed that you work with the SK, but you also work with other telescopes, including I think the Murchison Radio Astronomy Observatory. Can you give us a bit of background or understanding about what work that you do with those different telescopes?
Yeah, so in Western Australia, we have the Murchison Radio Astronomy Observatory. It's a land where we built already some precursors, and Murchison Wildfield Array, MWA, is the precursor for that. Actually, if you'd like to see, maybe next slide, we'll show you the picture of how Murchison,
Oh, wow,
so
amazing.
The spider-looking antennas that I took this picture in the field, it's a trial of MWA. So it started operating 10 years ago. So last year we celebrated 10 years since it started operating. SKA, the Square Kilometre Array, is an idea of the largest radio astronomy observatory in the world, came out maybe more than 20 years ago. And it took a lot of time to go from the initial concept to actually design, then choosing the countries that will be hosting the telescope, to actually now it's under construction, and the construction will end around 2030. So it's a massive project, and it needs a lot of knowledge, a lot of experience. To get that experience, in engineering, we take baby steps. We cannot just start from zero and then build the largest radio astronomy observatory. So MWA is a precursor, meaning that it really helped us to learn which type of cable we should use on the ground, because the UV is very strong, the temperatures are really high in the desert. So Murchison is up north. So it was actually a telescope that was used to learn about building radio astronomy in the desert.
Amazing.
And yeah, well, at the bottom picture, you see an engineering development array. Well, actually, it's a verification system. Engineering verification systems. We built a few of those, and this is one of the latest. It's one of the stations of the SKA, and there are 256 antennas in that circle.
Oh, wow. That's incredible. And so it's currently still being developed. Do you know like how many more antennas we're going to get? And do we have a timeline, I guess, of when that's going to be completed?
Yes, originally there will be, the design says there will be 512 stations with 256 antennas in each station. When I go overseas and present progress in my research with regards to this array, people get mind blown because they understand it's a lot of troubleshooting. A lot of potential issues. It's a really difficult project, but also the sensitivity that we will get will allow us to look back to the origin of the universe, back to the epoch of reionization and the cosmic dawn. So it's really exciting. And just to give a perspective, it's like a time machine that will help us look at 13.8 billion years ago.
That is honestly mind-blowing. I can feel my brain tingling as a result. Just touching on the MWA, I think I saw something from last year linking back with your love of art and creativity. Is it true that you actually worked as part of the MWA with the Yamaji Art Center in a collaboration where you designed the MW antenna beam that was later painted for Indigenous artists? Can you talk a little bit about that?
Yes, actually, I have a report here. So actually, how it started, I was working on the visualization. Actually, the started is we have the ICP, the Innovation Center of Perth, that had some people who were interns, and they one of the interns was an 3D artist, and he was looking for opportunities and projects. And I thought, look, electromagnetic waves cannot be seen, and it's always difficult to teach it without showing the visualization. And the visualization that I can do, will be taken from this commercial software that we use for actually CAD that I mentioned, computer-aided design. And they are not as exciting as potentially they can be. So in this slide, you see on the right, there are two beams. One is pointing up to the sky, another is pointing off. And they represent the beam of one station. So he helped me, and at that time I had a colleague. Then we were discussing we had a storyboard, what the video will have, how we're going to zoom in, zoom out. And then during those discussions, someone mentioned the 3D printing, and we thought, why don't we 3D print? So we 3D printed the beam, and then when people saw that, people from management, they got really excited because no one has ever printed a 3D beam of an antenna before. And beams of the MWA and the SK, they are amazing because there are so many antennas that constructed, so there are so many side lobes. So so you're talking about this amazing beam that was painted. It's amazing how I really like the colors, and the collaboration is just something you cannot even conceptualize. It just happened.
Yeah, I mean, that was I think the last thing I was expecting when I was just doing a little bit of research to prepare for this. But it was incredible. It's look, it almost looks like a little flower that's been opening up. And then you've got Indigenous artists who are painting using Aboriginal dot painting. But it's really interesting because, like you mentioned, that the beam pattern illustrates how the MW telescope, and I'm guessing it can point in different directions without having moving parts, which is a little bit unlike the ASKP dish. And so can you give us a little bit of understanding of what's the benefit of that, of being able to move in that way?
Yeah, this technology that's called aperture rays, they are not your traditional dish antenna that everyone knows, radio astronomy or telescope that is a dish. So SCAP definitely can point the beam, but it has to be moved. So when you move a large object like this, you cannot instantly switch the beam. There is some delay.
Yeah.
And also the cost of the telescope grows as the size grows. To see back to 13.8 billion years ago, we need to look at radio frequencies, which is, as a SK law, covers from 50 megahertz to 350 megahertz. The size of the dish that will be required to build that will be much more expensive compared to the return that it gives. There is a magic formula, rule of thumb, that tells you the cost versus the return. So therefore, those traditional dishes, they are super powerful, but for higher frequencies, the microwaves, for example, and higher. But when we're talking about the low frequencies, we use the aperture rays. Aperture rays have advantages that every single antenna is much cheaper, but of course, if you multiply it by 130,000, which is SK will have, it's a bit of a price.
It's expensive, yeah.
Yes, and the beam can be switched digitally at an instant. So you can point and repoint. Yeah, and also the way we perform in the simulations, we capture the interaction between antennas. That's called mutual coupling. And when we completed one simulation, we don't have to repeat the simulation if we want to switch the beam. So one simulation is enough. Once we have those patterns, the beams. I think it's the next slide. Let's try. Tell us about my research. Yeah, so on the bottom left, you see the exact beams of each antenna of the one of the arrays.
That actually, it looks beautiful, I have to admit. I was not expecting it to look so artistically pleasing.
Yeah, so the little bushes, little flowers, once you sum, digitally you sum up all the signals, you'll get the beam that was on the previous slide.
Okay,
and the single antenna is right there on top. It's on the left is a picture of one antenna. We call it informally a Christmas tree. It's actually a log periodic antenna. And on the right, it's its digital twin.
Oh, okay. So you mentioned that before, the digital twin.
Yeah.
So I guess with the digital twin, are you able to then try and test things out without, like, in theory, is that the idea?
Absolutely. So the beam that you see is a third from the left. You see the antenna, and there is the green halo there. So this is the beam that the artist created using the actual beam from the software, the industry standard commercial software. So to get that beam to the observing pipelines, there are two ways. You can either simulate it accurately and be sure that you simulated it accurately, or you can go to the field and measure it. But good luck with that, because it's a really expensive thing to do. And too much, yeah. So thanks to the codes, thanks to the high performance computing, we can actually now do everything on the computer. And then we're very safe making the assumption that our simulations are correct. And then those beams go into the processing pipelines.
Amazing. So speaking of your research, I understand that you were awarded the 2023 Department of Defense Eureka Prize for Outstanding Science and Safeguarding Australia. So first of all, congratulations. Can you explain what that research was for and how it can help improve life on Earth for Australians?
Yeah, so it is based on the research that I've done before moving to Perth. So after moving from Russia, I moved directly to Sydney and did my PhD there at Macquarie University. And my supervisor, Professor Carusel, is a very distinguished professor, one of the top in Australia in my field. He had the vision of that we are going to create this beam steering antenna that will establish communication with space for it will be mounted, so it will be flat and it will be mounted on moving vehicles. So you can straight away think about defense applications, how people that are in the middle of the desert and they using obviously the moving vehicles and they need to communicate, so they can communicate directly to space. And he assigned different projects to the group of students, and I was one of those, to design parts of that. And when I was doing my PhD, I didn't know that he had the vision. Only maybe 3 years after, closer to the completion of my PhD, I realized that, well, actually what we're doing, we're actually building a whole system. Wow. So this system will allow communication not only to the defense applications, but also to the people who don't have the access to the internet, to have it through the satellite communication. That is the beam steering technology, and our team is called meta steerers, meaning we use the metamaterial technology to realize the beam steering for satellite communication.
I mean, that's really amazing. Is there any new or current, are you working on any new projects or current projects that you're excited about at the moment?
Yes, I'm very excited about the project. It uses the machine learning and in particular neural networks to help us perform those simulations for the SK much faster. And neural networks and AI is very popular and used everywhere right now. It's not the reason I am interested in that. The reason is that I actually see that we have the bottleneck is the long simulation time that it takes to create those beams, to simulate them. So if we have the simulations much faster, then we can progress the project faster. And it's just really natural to use the technology, I mean the AI and neural networks in antennas, because it all can be modeled online. And for example, in the design of the antenna, whether it's this SK antenna that you can see, it has so many elements. The way it was designed without AI, without neural network, it was just a few years of redoing lots of things. For example, the low part of the antenna was only added as a last step. There are several iterations that's called skull antenna, 4.1, 4.2. So it could have been done faster if we just used the codes that would help us to find those optimal points. For example, which geometry gives us the right performance. So I have observed before that as an RF engineer, you tweak and tune and do a lot of fine tuning, which it takes a lot of time. So instead of this, it's much more efficient to use optimization and neural networks to do that. So right now, I have an intern that started with me in January, and she's a data science master's student, graduated from Curtin University. And the first part of the project that is almost done was in relation to the beams. So we created lots of models that we trained to actually create those beams. And the second thing we'll be learning how to generate the predictive neural network to actually design antennas. It's like next level.
Wow. So it's, in a way, is it that the AI is, you're training the AI, you're developing the neural networks, and then is the AI developing or telling you, oh, this is where you should put the satellite, this way you should put the antennas, instead of having, you would still double check it as the engineer, but it's cutting down a lot of the repetitive and manual processes?
Yes, it's a design automation.
Amazing. That sounds
like
a powerful.
There. Yeah, but I hope, yes, at least it will help us with finding non-intuitive configurations, the things that are novel that we didn't think of.
That's honestly sounds not just only exciting, which I know I've been saying amazing, wow, and exciting, but this is such cutting edge technology and research that you're doing. Looking back, as your younger self, what would you have told your younger self now that you're in this current position in terms of, I guess, career advice, and then also what would you tell someone who wants to get into the space industry? what would you wish you had known when you were younger?
I was not so confident when I was presenting my work, and I think there was a reason for that I didn't have so much expertise that was under my feet to be confident. But now when I work with students, I see that they have done, for example, they can do a lot of really nice work, but when they present, they're scared. And just yesterday, I had a training, help my student to prepare for the final year presentation that was just happening today in the morning. And I told her that stop being scared, being confident. I know you've done great work. So yes, being confident and taking opportunities. But I'm very lucky that the way I was raised, I was told never say no. If there is an opportunity and you feel like you cannot do it, you say yes, and then later you will do it. So really a brave approach.
Yeah.
To anyone who wants or is fascinated about space, I would say have your basics, have fundamentals. You really have to be good at math and physics, programming. So it is a lot of work. And to get to the level when you can actually be really confident, yes, you need to know that you've done your work. So study hard.
Some solid advice. So I would now like to open to move on to some of the questions from our audience. So for everyone watching, please post your questions for Dr. Maria Kovaleva, in the Teams Q&A. And while we're just waiting for some of those questions to come through, are there any other things that you'd like to cover or share with the audience today?
Yeah, I would like to share a little bit about, in the next slide, about my Fulbright experience.
Oh, yes.
And okay, so this is teaching electromagnetics. I've been working at the University of Sydney. Yeah, so, teaching, it's pretty straightforward. So in 2022, I got a scholarship to go to the United States for 4 months. And,
congratulations.
Thank you.
That's a very prestigious scholarship.
It is, yes, and it was really great experience. I learned a lot. Just moving from Russia to Australia was a step, but I was a bit younger, so and lots of enthusiasm, didn't know what I was doing. And actually going to the US to do my research was eye-opening to collaborate with people there. The way that the Americans work is a bit different to how Australians work. There's a lot of collaboration happening there. People are very friendly. So it was a great experience. So if you're watching this and you're also doing your degree, undergraduate and master's, just read about Fulbright and go to the website, find the deadlines, and maybe not this year, but next year you can apply. Just try. It's a wonderful experience. And the next slide shows a little bit of my hobbies, what I do in my spare time. I like traveling. I still dance. I really like flamenco. This year I managed to go to Spain because there was a conference there, and I visited, in addition to being at the conference, which was in actually Canary Islands, I organized a few visits to Madrid and Seville to go to universities and give lectures about the SK. It was wonderful. So I got to see flamenco in the evening. And I like the ocean. I like traveling, doing scuba diving. And when there was COVID, I also tried pottery.
Wow. So you're just like an all-rounder, incredible person, super smart. And then So is that another, I guess, example you would give to students and others who are interested in getting into the industries to try and have like diverse experiences and also not just focus on studying, but continue to have your like extracurricular activities?
Absolutely. Science, there is already, it's proven that you have to take breaks. You cannot be in your codes all the time, in your writing, or study. You have to take breaks and switch between mental activity and physical activity. You have to socialize, because when you go socialize, when you go have a healthy sleep, your brain still works and you still, it's processing that. So never exhaust yourself, enjoy your life. That's the most important thing. It's important. to do diversity.
Amazing. I think we might have a couple of questions. The other question actually that I have is, you mentioned a little bit about machine learning, AI, and how that is helping to, I would say, fast track some of the work that you're doing. What do you think is, I guess, what are the biggest challenges for Australia and for humanity in space, and how do you think we'll overcome these? And do you think that machine learning and AI might help us with those challenges? I know it's you don't necessarily have to know the answer, but just would love to know your thoughts on this topic.
Well, AI brings lots of solutions, and for example, ChatGPT can be very useful, but we have to keep being accountable about all our intentions. So challenges for Australia and humanity in space is actually continue being friendly to each other, because right now there are no regulations, and we have to be accountable of using that freedom for the positive purpose. Yeah, we have only one planet so far. It's super exciting that we have Australian Moon and Mars initiation and the grants for that exploration and Moon and going to Mars, but we live on Earth and we have to take care of it. So we have to use AI and space peacefully. That's very important. I don't think that AI is actually helping with that, because it's another space with freedom. So it does bring dangers. But yeah, in that sense, being aware, self-aware, and mindfulness, I think that will help.
I think that we have maybe time for one more question, and then we'll have to wrap up. But what do you imagine the future for Australia in space will look like in 2030? So it's almost the end of 2024, in about a little bit over 5 years' time. What do you imagine that future will look like for us, or were you hoping to imagine the future for space in Australia would look like?
Well, obviously, because I am a part of the SKA, I'm looking forward to its completion. But before it's completed, there will already now there are 2 stations that have been correlated. So we have first results. In a few years, by 2030, we'll definitely have more results, more fascinating signals that we can detect. So lots of data that needs to be then processed in an efficient way to make the discoveries and reach further in time. For space, right now there is a development of the CubeSats. So CubeSats are small satellites. They're a size of a cube. As a 1 unit is 10 by 10 by 10 centimeters. And at Curtin University, we have an amazing binary team that launched already 2 versions of those CubeSats. And we have some grants that we submitted with them. Hopefully, we'll get to work in the future with them and send the 3rd and next generation of the satellite of the CubeSats to space to do the surveying, or later to the Moon, hopefully. So it's a good time to join the space industry. What I would like to see more is funding, of course, because if we have funding, then we can hire students to stay in academia, stay as postdocs or research assistants, because I think it's for the entire country, but especially for Western Australia, we lose students after. I had so many good students, but they go to the jobs which pay a bit more. So I would like to see fair pay for our sector too. Yeah, so encourage. And I think it's already happening. There are some local fundings that are available for the students. Just I hope that will increase and continue like that.
Well, thank you so much.
Thank you for having me.
I agree. Yeah, I agree that those are all great hopes, and hopefully goals that will be fulfilled in the next few years. I believe that's all the time that we have for today. Thank you so much for joining us and listening to our space guest, Dr. Maria Kovaleva, and thank you so much for sharing your story with us. It's been fantastic hearing about your diverse experiences and also what you like to do, in your free time. For the audience, if you would like to learn more about space in Australia or how to become a space expert, please come visit us at the Australian Space Discovery Centre. Thank you so much, everyone.
Thank you.
Right,
Thank you for the interview. I totally enjoyed it. Bye-bye.
Yeah.